Welcome everybody. My name is Tarani Chandola. I'm the director of the Methods Hub here at the University of Hong Kong. And it's my great pleasure to welcome Dr. Jose Pina-Sanchez to our first Methods Hub seminar of the academic year. Welcome, Dr. Pina-Sanchez. And Jose is an associate professor in quantitative criminology. And he's definitely got a really interesting multidisciplinary background. He has an undergraduate degree in economics, and then a master's, and then a PhD in social statistics, and then is trained to be a criminologist as well. I'm really, really happy that he's going to talk to us about some aspects of his research, especially the methodological aspects related to measurement error. And I'm also going to warn you that that Jose does have one or two questions where he wants a response from you as the attendees. So please don't be shy in responding to his question that he poses. Or if you are shy, you don't want to respond, you can always use the chat. He's also said that he's very happy for people to, if you've got questions, perhaps if you feel shy in interrupting, you can definitely put them in the chat. And if he hasn't seen that, I'm more than happy to relay those questions to him. So we want this session to be as interactive as possible. So please don't feel shy in putting forward your questions. Okay. So Jose, take it away. Thank you.
Right, thanks. Thanks a lot, Tarani, for the introduction and for giving me the platform, for inviting me today to talk about what I would say is not a sexy topic. I'm going to be talking about measurement error. It's not it can be seen as a dry topic, but I really think it's a massive methodological issue that we tend to neglect. So it's a very important topic. So I'm really happy that I've been invited, to speak. I didn't know it was going to be the first in the year. Well, I suppose it's the start of the year for your Methods Hub. And yeah, I'm really happy that all of you have made time to come and listen to this talk today. So I'm going to try to share my screen now. All right, here we go. And I'm going to expand this. I'm not going to be able to look at the chat. I'll just see my slides. But as Tarani said, I think I've timed myself so I don't speak for longer than 50 minutes. So we still have plenty of time for questions. So if you feel that there's something that, that is particularly curious, or, it's not well explained, or something that, that relates to your own field of research, or you've got any burning questions, don't hesitate at stopping me. And then we can make stuff, and discuss points as we go along, really. I think that will be a bit more, a bit more easygoing, really, than having me lecturing. But yeah, as Tarani said, I've got a question for you at slide 11. So in the middle of the talk, I've got a question for you. I want to see how you will answer. I'm not testing you. It's just so we can see, well, basically, so we can illustrate how pervasive this problem is of measurement error, and how difficult to anticipate and to see what kind of impact it's going to have. Right. Okay, but I'm getting ahead of myself. So yeah, thanks everyone. Thanks for being here. Thanks for the invite. I'm going to be talking about measurement error. This is going to be a very, very introductory talk to the topic. And to make it more engaging and more framed, I'm going to be drawing on examples from a little bit of different subjects, but I'm going to be drawing predominantly from a particular question, which is measurement error in police statistics. And the reason why I'm doing so is because over the last couple of years, I've been part of a project funded by the Economic and Social Research Council from the UK. And it's a project that has been led by Ian Branton-Smith from the University of Surrey, and that we've undertaken in collaboration with Alex Arnott and David Will-Hill from Manchester. So yeah, we've been working quite a lot of that. So I will use what we've uncovered from that project to kind of illustrate some of the points that I want to make. Now, in that project, what we did was to structure it in 3 different ways, or according to 3 different pillars. First, we tried to assess the prevalence of measurement error in police statistics. Then we tried to assess what kind of impact it has. So when you use that data, how will that impact your findings? And then we try, at the end of the project, we try to suggest different ways to adjust for the impact, right? I mean, to try to, minimize the bias as much as possible. So I'm going to follow that same structure here as I introduce the topic of measurement error. Okay, so let's get started. Very from a very simple standpoint, really, without getting into deep epistemological debates, how do we define measurement error? Well, the way I see it, I mean, the simplest way to see it really is as the discrepancy between the true value that we want to observe and what we end up observing. So discrepancy between the true and observed value. When we can anticipate that they are not exactly the same, that's what we call as measurement error. And normally when we think about why does this happen, and again, oversimplifying things, we can think of two main reasons really. This will be, or three really. This will be very prevalent when we're dealing with constructs, as it is often the case in social sciences, with constructs that are subjective, elusive, difficult to define, or difficult to operationalize. And also, we should expect this to be a problem also when we are dealing with more a kind of like objective concepts or more factual constructs, but that are nonetheless, the measurement process is nonetheless flawed. So let me give you some examples. So when I'm talking about elusive constructs, things that we care about as social scientists, measuring happiness, ethnicity, political decentralization, those are some of the many different things that we care about that are elusive really, and for which often there is not an agreed definition. Therefore, it's going to be difficult to measure, right? And therefore, we should expect measurement error in those in those instances. But as I was saying before, that's not always the only remit or the only area where we should expect measurement error. We should also expect it when we're looking at more factual information, like for example, when we're counting events, like how many times did you go to a pub last week or last month? How many times did you go to eat out in a restaurant, for example? Or also when we're measuring duration. For example, when we ask people, for how long they've been employed or for how long they've been unemployed, actually, we should expect measurement error there. And the reason is because often, we elicit this data, we retrieve this information from subjective means. And we ask people, and in particular, if we ask them face-to-face, right? Well, actually, we ask them through self-completed questionnaire, we can see different types of errors, like memory failures, recall errors, social desirability, acquiescence bias. All of those kind of biases will lead to measurement error, right? And the third realm where we should expect also measurement error is when we use proxies. So very often we want to use something in our study, like we want to have poverty, that's what we care about, or maybe violence in society, but we don't have a measure for that because these are difficult things to measure, right? So we rely on proxies like earnings or wealth for poverty, or crime statistics from the police when we want to look at violence. Now, when we use those proxies, we should expect measurement error, right? Okay, so let me just illustrate this a little bit with a bit more detail. Talking again, focusing on this thing that I was talking about, like police statistics. So in this project, the Recounting Crime project, so I think I'll be able to share I'll be able to share the slides with you. So here there is a link. If you click on it, you can get into our project's website. Okay, so the first thing we did in this project is to try to document how much measurement error there is in police statistics. Because when people use this kind of like crime data that comes from the police, most people really are all researchers. When they're looking at that, they really are referring to all crime taking place in society. However, crime statistics from the police, they are a very, very, very small subset of the total amount of crime. So they're going to be affected by what is known as systematic errors. And that's not just it. So what we know the major issue is there is underreporting. Not everyone reports crime to the police. Then there is under-recording. Not all crime gets recorded. But also there are recording inconsistencies across police forces or police officers. So there are quite many different, and that's not just it. There is also like political pressures that also affect the recording process and many other things. But the point is that there are multiple measurement error mechanisms. So we shouldn't really trust this data as face value. Okay, so that's just an introduction to what is measurement error. So why does it matter? Why do I feel so strong that that we need to care about this? Well, the first thing is obvious, right? I mean, if the data we're using is affected by measurement error, we cannot use descriptive statistics accurately, right? I mean, we cannot describe reality. If we're using police statistics, we cannot know what is the true prevalence of crime in Hong Kong, really. Or if we do, we should at least use caveats, right? I mean, because we know that's not going to be an accurate measurement. We don't know, we cannot describe reality. We cannot see, how things change across time or make comparisons between places like Hong Kong or Macau. And that, I think, is straightforward. Everyone can see that the measurement error affects your descriptive statistics. What is normally not so commonly understood is that also when you've got measurement error, that can also affect any kind of causal inferences or measures of association you want to explore between different concepts. So going back to the question of crime, A lot of my colleagues are looking, for example, at what is the effect of unemployment on crime, or the other way around, seeing crime as a cause rather than as an effect. Many researchers are looking what is the impact of crime on mental health or health inequalities. Okay, so all those kind of research questions are going to be biased because there is, if we use police data, right, or if we use a measure, a variable that is affected by measurement error. That's the bad news, right? But it's good to be confronted with bad news so we can do something about it. And that's the truth. I mean, there's so much more that we could be doing. If we know how to define the measurement error, if we know how to expect it, if we expect it and acknowledge it, then we can start measuring, assessing its prevalence. And from there, we can jump into assessing what kind of impact it's going to have, and then possibly find ways to adjust for it. But in order to do so, we first need to, the first thing we need to consider is look at how much measurement error there is and what type of measurement error there is in the variable that you are dealing with. So in order to do so, what I'm going to do now is consider different measurement error models. So measurement error models, we could think of these as kind of measurement error mechanisms. So let me illustrate what I mean a bit more formally. So one way, normally, when we talk about measurement error, very commonly in the kind of applications used in the literature, most people assume that the errors are just due to random processes. So this is normally illustrated with what we know as the classical measurement error model. That's, as I'm saying, the most common perception, or how to say, representation of measurement error in the literature, really. And how it works, the assumptions upon this is built is the idea that instead of seeing the true value, x, what we observe is x asterisk, which is the true value plus some noise, right? And if we assume that that noise is entirely random, then it can be represented like that formally, or visually we can see it like that, right? That's the true value. The center of the bullseye is what we're trying to measure. But because whatever the measurement process is imperfect and it's affected by random errors, we take different observations that are not exactly accurate, right? They are affected by noise. So we can think of many examples. For example, like a scale that is not very reliable. Like I think I am now 68 kilos. So, if I was using a non-reliable scale, maybe one day I'm 69, the next day I'm 67, right? 68. I will always be floating around my true value, my true weight. You can also think the same way about like math test or literature or language test, English test. Like depending on how the pupil is doing that day, whether, they had a big breakfast, whether they had a good night of rest, they will do better or worse. And that's got nothing to do with their, that's got nothing to do with their maths ability, really. So there is some noise in that measurement process. And similarly, we can see the same thing going on in police statistics, depending on how the police officer is feeling that day, depending on how they use the discretion to assess whether a crime is a crime or it isn't, or it's just, an assault or a robbery or something like that. There will be inconsistencies, right? Okay, now, if we think of measurement error like that, which is the most common way, we can think, since it's entirely random, we see that it doesn't affect the mean of the variable that we're measuring. So x asterisk is the mean of x asterisk is the mean of x, is unaffected. However, we've got some extra noise. So there's some added variability, right? That's the only effect it has on descriptive statistics. And that's good very often. That can be used to reflect, many of the measurement error mechanisms that we see in reality, but not all. I mean, the truth is that this measurement error model is overused because of its simplicity. It's straightforward to use. Very often, what we see is what is known as systematic errors. So in this case, we can represent them under the same functional form, but now if we assume that this is systematic, the average would be different from zero. So it could be below zero when we are underreporting or underestimating the true value, or above zero when we are overestimating the true value. So again, we can think of many different examples. Going back to the police statistics, if there's underreporting of crime, normally we should expect police statistics to be measured down here. So not being able to measure, like not being able to target the mean, really, the true extent of crime. We could also think the same, when this is very prevalent when you think about social desirability in surveys. So when we use questionnaires, and in particular when we've got face-to-face, when the mode of collection is face-to-face, we should expect, like systematic biases, right? I mean, for example, when we're asked whether we like to live with foreigners, well, no one has an issue normally, right? I mean, in surveys, but that's because there is a lot of those social desirability. Or maybe an even clearer example, when you ask people, how many sexual partners they've had in the past throughout their lifetime, if you ask men, there's going to be positive systematic errors. They're always going to be over-reporting the number of sexual partners. But if you ask women, they're going to be, negative systematic errors, right? They're going to be underestimating that. Okay, so those are just examples of systematic errors. Let me just go and check that I'm doing okay in terms of time. I think I'm doing good so far. Okay, do you have any questions? Let me just check the chat. No questions so far. Are we doing okay? Are you still all with me? Yep. All right. So I'll continue in that case. All right. Thanks for the thumbs up. Cool. All right. Let me expand this. All right. So, but that's not all. I've talked about random errors, about systematic errors. But so far, we're assuming that the errors are independent of the true value. And that's not always going to be the case. One case in which that's questionable is when the errors are proportional to the true value. When would that be the case? Well, that tends to be the case when we're thinking about memory failures or recall errors. When we've got count data, duration data, you can think that, the more, when we're trying to elicit, the number of times something happens, and we're relying on people's memories, really, we should expect that if something is rare, they should be able to report that it's rare. But when something is frequent, they will report more inaccurately, right? I mean, think about this. Think, for example, about this question. How many alcoholic drinks did you have last week or last month? So those of you who didn't have a single one, will be very accurate in reporting as 0. Those of you who had 30 or 20, I don't know, like a big number, right? Will not be so sure, right? We provide an approximate measure. And so those in between, might be able, again, to provide a better measurement. Maybe alcohol is not the best example because clearly alcohol impairs your memory, right? But let's think about, like eating out, or how many times you've been to a restaurant last year. If you never do it, you'll report it very well. But if you do it quite commonly, it will be pretty difficult, right? So in those cases, we should expect the measurement error to be proportional to the true value. And now, how can we represent that? Well, we abandon this additive model from the classical measurement error representation of measurement error, and then we can consider like a multiplicative model where the two are proportional to each other. If this goes up, sorry, if the true value goes up, we should expect that one to go up too. Or no, we should expect, sorry, not the effect of the measurement error on the observed to go up. Okay. And then to make it worse, I mean, those are just ways of simplifying, measurement error mechanisms so we can think of them, right? I mean, but in reality, what we see is that reality is way messier than that, right? And rarely there is a single measurement error mechanism so cleanly described by one of these models, taking place in reality, right? I mean, and going back to our question of measurement error in crime data, what we theorize and we expected to see, and then we corroborated empirically, is that there could be systematic errors. That's the clearest type of error because crime is underreported. Not everyone reports crimes to the police for different reasons, because you feel guilty, don't have the time, convenience, many different reasons, or don't trust in the police. And then we should also expect random errors because, it's a very, after all, recording crime is a kind of like idiosyncratic, not idiosyncratic, but there is a lot of, how to put this, discretion from the point of view of the police. So we should expect that there are like random processes there that will increase the variability in the recording of crime. And then what we also argued is that we should expect this to be multiplicative, because at the end of the day, when we are deriving crime, or when we're measuring crime, or as it is recorded, it's recorded as count data. So we would expect in areas where there is more crime to see more measurement error. And that's what we expected. So what we did was go ahead and test that empirically. So, and that's what we're doing here. I mean, that's what I'm showing you here. So what we did was to plot, crime rates from different 42 police force areas in England and Wales. We were looking at all property crime to get, big samples, so there is not a lot of sampling error. We look at data from the Home Office, so that's from the police, and we plotted that against crime rates in the same area, but derived from victimization surveys. So in particular, the crime survey for England and Wales, where we're asking people, whether they've been victims of crime or not. So this is a much more accurate, it's not a gold standard, but it's a much more accurate measure of the true extent of crime. So when we plot the two of them together, what we do now is try to describe what is the best measurement error model. What is the measurement error model that provides a better fit here? And what kind of mechanisms, measurement error mechanisms, we could kind of like elicit from here. So if we impose this kind of like classical measurement error model, assuming random errors, we would expect, and no systematic errors, we should expect all these dots, right, to be floating around that line. But that's not the case, clearly, right? Because there are systematic errors, because there is underreporting, they all fall to the right? There's underreporting in all of them. Okay, so then we can say, all right, so it's not all random. There's also systematic error. Well, that's what we go and contrast now. And we see that, yeah, we create this other measurement error model where we say it's an additive measurement error model. And, you know, we allow for systematic errors. And that provides a better fit of what's going on here. But still, it's pretty bad, really. So it's better than all things being random, but it's not great. Then what we do is try this multiplicative model with systematic errors. And then we see a much better fit. Actually, the fit it seems to be like this, seems to be like a very good representation of what's going on. And when we define measurement error in crime statistics that way, and then we plot the differences from that line to what we see, then we see that the errors are normally distributed. And we see that on average, we're only recording about a third of all property crime that is taking place in reality. And that's in England and Wales, and that was like a decade ago. Things might have changed, but that's how we can represent that. You know, we can be fairly certain that, you know, like this is a good representation of measurement error in police statistics, systematic, random, and multiplicative. Okay, so once we nail that, then we can start thinking about what kind of impact we should expect. Okay. So far, I've shown you how we've seen how different types of measurement error mechanisms can affect your descriptive statistics differently, right? I mean, systematic errors will affect the mean, random errors will affect the variability or measures of dispersion. But what is, and that's, I think, as I was saying before, I think that's pretty straightforward. If you've got a good understanding of the subject, all of you will be able to anticipate how much, you know, those type of errors are affecting, you know, the variables that you care about, right, that you use in your own research. Now, what is a lot harder, or can be a little bit hard, well, definitely harder, is to see what kind of impact those measurement error mechanisms might be having on your kind of regression models or measures of association, say, even if you are just looking at correlations, really, bivariate correlations. And because things get a little bit messier now. So there are a lot of things that could be going on there that will define what kind of bias you should be expecting. So first of all is what kind of outcome model, you know, your substantive model of interest. Is it a linear model? Is it a logit model, Poisson, you know, a multivariate? That will define the bias that you should expect in your regression coefficients. The other thing, of course, is the measurement error model. You know, what are the mechanisms? Is it additive, random, systematic, multiplicative? And then another crucial thing is, where is this variable that is affected by measurement error introduced in the model? Is it introduced as the response or outcome variable, as the explanatory variable? Is it transformed before it is introduced? If so, how? Log transform? Do you take the square root? All of those choices will affect the bias that you should be able to see. Okay, so here's where my question is going to come. I'm letting you know in advance, so you're all aware. Okay, so just to see, you know, just to illustrate how variable the impact can be, we're going to see a very, very simple setting, simple scenario. This is just we're going to see how measurement error can impact the findings of a simple linear regression model. So let's assume that this is the model we care about, and we want to look at the effect of X on Y, and we want to kind of derive a causal effect, right? So we really care about that beta. We really care about estimating that beta accurately. Okay, but now I'm going to give you 4 different scenarios in which, you know, things will vary. So in the first one, we could expect, you know, like we will be expecting that there is some random error, so classical measurement error, affecting your Y, your outcome variable, right? So it's additive and it's random. It doesn't have any systematic components. Then I want to review a second scenario. The same kind of errors, same errors as before, but now affecting the explanatory variable, not the outcome variable. Then in the third scenario, we go back to the outcome variable, but now the errors are not random, they're systematic. You could think of this even as a scalar, like U being a scalar, like being a particular value by which all observations of Y are affected or modified. And then a fourth scenario where, you know, you also have systematic errors, but now the errors are multiplicative, as I showed you before. So they're not additive, they're multiplicative. And here's my question. So how, and really, I'm not really testing anyone, and probably many of you will know the answer, really. So I'm not trying to be clever, appear clever, or test you in any way. I just want to get a conversation started. So in which of these 4 scenarios would you expect the beta to be biased? In all of them, in none of them, only when there's systematic errors, in 1 but not in 2, in 4, right? I'm gonna see in the chat and see if any one of you have dared to reply to that.
Jose, there's already a question in the chat. I don't know if you can see it.
Right. No, I cannot see it. I've got the chat in front of me. So can you read it, maybe?
It's in the Q&A section in case you can't see it. So
I've got chat here, but let me see. Yeah, Q&A. Yeah. Okay, I'm sorry, I don't understand why the mean of noise equal to 0 for random errors, but not systematic errors. Could just, yeah. So what I mean, going back to how when I was defining systematic and random errors. So the mean 0 here means that on average, there's an error term, which is, we could think of this as a variable, but on average, the variable has got an average of 0, right? So you could think of this as a normal distribution with mean 0 and a certain, a standard deviation, a given standard deviation, right? So that's what you expect to see with random errors, right? So basically, they are not pushing away, when you've got random errors, your observed value on average is not pushed away from the average of the true value. What you have is just more noise, right? So let's think about examples like that scale that is not biased, but is not reliable either, right? I mean, on average, if you measure yourself in that scale 100 times and you calculate the average, it will give you your average weight and your accurate weight, right? But every single observation will be affected by noise, right? You follow me, right, on that? I think it's always the best thing to do is to talk about examples. Now, this is different when you've got systematic errors. So when you've got systematic errors, if you repeat the same measurement process, because the error is systematic, right? The average of that observed value of X that is affected by systematic errors, the average of that observed value will always be away from the average of the true value. So we could think again about, for example, sexual partners. I mean, if you ask the same person about, how many sexual partners they've had over, 100 different days, you repeat the same observation process, and let's assume that, their sexual activity has stayed the same, right? They will always overestimate, right? If it's a man, overestimate the true value, right? And if you take the average of that, of those observed values, right, of those answers that you're getting, they're going to be on average away from the true value. So it doesn't matter how many times you take the same measurement process, it's always going to be biased. The mean is always going to be biased because the nature of the mechanism, or the measurement error mechanism, which is systematic and it's not random. Is that more or less okay? Am I answering your question? All right, fantastic, great, cool. Okay, let me see if I can go back to Q&A. I've got that. Okay, so I don't see anything, not even you, Tarani. So you don't provide me any answer. Let's go back to the scenarios. Tarani, you are pretty much forced to give an answer here. So where would you expect to see a beta to be biased according to these 4 scenarios?
Oh God, so yeah, so probably the last one with the multiplicative, where we've got the measurement error in the y variable, in the dependent variable. We've got multiplicative errors affecting response variable. Systematic additive. Maybe, yeah, also for the second last one, systematic additive errors affecting the response.
So the last 2, right? Systematic is pretty pervasive, right? Systematic is bad news in most, and I agree, yeah. Okay, but and why I wanted to, to make you talk, right? I make you think about these things is because when I work on these topics, what strikes me the most is how variable and unexpected, really, the problem is, how difficult to anticipate the problem is. Okay, so let's review each one of them one by one. So the first one, where we had a simple linear model, we've got an outcome variable affected by random errors. So these kind of random errors, right, which have got a mean of 0 and some, it's just random noise, if you want, white noise. So what happens here? Well, we can substitute, this observed value and then rearrange. Now let's substitute. We know that y asterisk, assuming that our measurement error model is accurate. So we define it like this, right? And then when we rearrange, we take that error term, measurement error term, which is random, and move it to the right. Now, when we do that, because it's random, it has a mean of 0, it's not going to affect the constant, nor is it going to affect, the regression coefficient. What it does actually is that measurement error is absorbed by the epsilon, right, which represents the error term in the outcome model of interest. So that's just your residuals, right? So your residuals are going to be inflated, which means that you're going to lose some precision in your model. Of course, you're going to lose precision because, like the measurement of your outcome variable is measured with imprecision, right? It's unreliable. But that's all, really. That's all going to be, beta is going to remain unbiased, right? And the best way to see this is with simulated, visually, really. So I'm going to show you some data that it's all completely made up, right? But it illustrates the point. So here I'm plotting you values of y against x, and we can assume that, the correlation between those two variables is very high, right? But we don't observe y. We start, we observe y asterisk. So in other words, what I'm going to do now is try to add a little bit of noise. So we see and random noise. So we see what kind of impact it's having on our relationship, right? So I'm not going to be moving, right? I mean, the dots on the horizontal line, I'm going to be moving them on the vertical line, because what I'm going to do now is that y is going to be more imprecisely measured, right? I'm going to add some measurement error. So these dots are going to move up and down, right? And I will do that incrementally, progressively. Okay, so we add a little bit of measurement error, like classical measurement error. So completely, random, just with a little bit of variance here. So we see, going back, this is what we had originally. This is what we have after adding a little bit of random noise to the y variable. And if we add some more, we have this. So you can see that, like the precision of the model is worsening, right? Our model doesn't do such a good job at summarizing the relationship. And we can add some more and some more, right? And you see the point that I was making before. We're losing precision. However, notice what happens with the blue line, right? It stays the same. The slope is unaffected, right? So the slope is that beta we were talking about. It's unaffected. So that remains unbiased, right? Under that scenario. Now, let's see what happens when now the same measurement error is affecting your explanatory variable, right? Your outcome variable. I was going to show this to you using formally, using algebra, but I realized that it's too boring and too complicated. And really, the best way to see this is, again, visually. So we've got the same data as before. I'm completely making it up. But now, what I'm going to be doing is I'm not going to affect the y variable. Now I'm going to affect the x variable by using, like classical measurement error, right? Random error. So what we're going to see is that these dots move left and right over the horizontal line because there is more imprecision, right, in x. So there's more variability due to the noise, right? And I'm going to do that progressively. And you let me know what you see, right? We lose a little bit of precision. If we increase the measurement error, we lose more precision. If we increase the measurement error, we lose more precision, right? Just as before. But on top of that, what happened here? All right, so I'll tell you, I was just checking the chat. Okay, so on top of losing precision, check the blue line. As we add more error, what happens to the blue line? We are basically changing, it's basically being biased by the random error in x. So what we see is that there's an attenuation bias associated with classical measurement error, with random error in x. And that is something that is a lot of people get wrong in the literature. A lot of people say, because the measurement error affecting my explanatory variable is random, that is not going to bias my regression coefficients. Well, with just this simple setting, we can see that's not the case. Depending on how much measurement error there is, you should expect a proportional kind of like attenuation bias. Okay, let's go now to a scenario 3, where we were saying, okay, we will go back to measurement error in y, but now it's systematic error, but it's still additive. So what we can do is, as before, substitute, rearrange. And now, because it's systematic, right? Because it has a mean that is different from 0, it's going to affect the constant. If there is also some variabilities on random errors, it's also going to affect the precision. But notice that it doesn't affect, right? When the systematic error is in the outcome variable and is additive, it doesn't affect your regression coefficient. So the causal estimate of interest remains unbiased. But let's now look, just to make it, the final leap. Let's now look at what happens when we've got the same measurement error, but now when we define it as multiplicative. When we've got that, we substitute, and then when we rearrange, a factor goes back, as a denominator, right? It's go as dividing rather than subtracting. And when it does that, it affects all the regression coefficients in the equation. So the residuals, the regression, the slope, and the constant. So all of them are affected proportionally to the extent of the systematic bias, really. So it's a mess, really. And the good thing here is that it's very easy to anticipate, right? If you can anticipate how much systematic error you can readjust that beta. But everything gets biased, right? So why I'm taking too long, really, to explain this is to go over this is to make this point that depending on the type of errors, we can see very different outcomes, really, from relatively negligible impacts or no bias at all to everything is wrong, really, to it's just a disaster, really. And remember that we've only considered really simple scenarios, really. In reality, things are much more complex, really. So that's why I really like this quote from Nagent, who portrays measurement error, borrowing a metaphor, as a gremlin hiding in the details of the research that can contaminate the entire set of estimated regression parameters. So whenever I think of measurement error, I like thinking of that gremlin, really, because one is unleashed, it can destroy, right? I mean, all your coefficients, but you never know, really. It could be there. You never know where it's gonna come up, really. And in some cases, it will be one of these brownish one, how is it called, gizmo, like it will be all good. But then when it turns gremlin, then it can destroy really your findings. And it's difficult to anticipate. That's the point that I wanted to make. So I think I'm taking too long, so I'm gonna skip this part. So how are we doing in terms of time? Tarani, do I have another 15 minutes or should I just speed up a little bit?
Yeah, I think you've got another 10, 12 minutes, so I don't think you should speed up too much.
Okay, all right, okay. Let me just then go over this quickly. So as I was saying, those scenarios that we reviewed are just, very, very simple scenarios. In reality, what we see, as we saw before, right, as explained before, is that, many of these mechanisms take place at the same time. So what we did in this project, in Recounting Crime, is try to anticipate what would be the impact of the kind of errors that we see affecting crime statistics, which, if you remember, were multiplicative, systematic, and random. So what we did was to run a model where we look at fear of crime, that's what we call worry, and we want to look at what is the effect of crime on fear of crime, so actual crime, but like for that we use police statistics, that's why it's got an asterisk. So we really want to look at how much bias there is on that. And then we've got another control, which is perceptions of disorder, right? And what we do is estimate this using victimization survey, so using like true value, and then we see what is the true estimate. And then what we do is simulate this kind of measurement error, types of measurement error on top of it, and try to report back what is the bias. So what we do is simulate increasing rates of under-recording systematic errors, and also increasing rates of random errors. Like in the first one, in that line, there is no random error. Here, there is moderate random error, and this is substantive random error. So what we see, if you go back to, if I can focus your view around here, which is normally, most crime it depends on the type of crime, but around 50% of it is underreported, right? So if that's what we expect, we should expect huge biases of about, at least 50%, the true estimate. So, our estimates of the effect of crime on perceptions of crime or worry is overestimated by 50%. Now, the other thing that we observe is that the types of biases that respond to different mechanisms go in opposite directions. So as we increase the level of under-recording, we've got augmentation bias. So we're overinflating the estimate. But also, as we increase the random error, there's attenuation bias, as we saw before. And those two are competing, right? So it's going to be very difficult when you've got the two measurement error mechanisms playing at the same time, It's going to be very difficult to see what is the exact impact. And that's what I meant before by the gremlin, really. Now, one thing we suggested in this project is to do something really simple. I mean, we are trying to do something more complicated, and I'll mention that at the end. But something that everyone could do is take, when you use crime statistics, or when you use anything that you think is affected by multiplicative errors, I think it's normally always a good idea to take a log transformation. And why is that? When you take a log transformation of a variable that is affected by multiplicative error, then what you're doing in reality, what you end up doing is turning the multiplicative model into an additive model. And that kind of like leads to less severe types of biases. So when we do the same thing, but only logging crime statistic, then we see that if there is no random error, there is absolutely no bias. And we can only see some bias if we think about, again, 50% of under recording, when we really have like really strong random errors taking place, a lot of variability between forces. But in reality, we will be somewhere around here in most cases. So the bias is much lower. It's about 0. So it's only 10% lower, the estimate, than the true estimate, right? I mean, so it's not what we had before, which were, like catastrophic scenarios that are difficult to anticipate. So that could be an easy fix that we should expect. Now, I'm going to cover now quickly, what we can do to make things better, really. So we've looked at, the prevalence. We've looked at the different measurement error models. We've looked at the impact that could be expected. Now, what can we do to deal with this? I mean, the first thing that we should always do, and no matter what, is always try to improve data collection processes, right? I mean, try to actually think carefully about our questionnaires, how they are designed, or how we're measuring, how we're operationalizing a concept, how we're defining it. Is it just based on convenience, or is it really because, are we thinking hard enough in getting the accurate measure that we want? That's, of course, always a given. But very often, in particular when we're dealing with secondary data, there is nothing we can do there, right? So what could we do then to try to adjust for the type of biases that I've been talking about? So we have seen how in some simple settings, we can anticipate what's going to be the impact and therefore adjust for it. That's going to be the case in some settings, really, in particular when we're dealing with linear models and kind of only one measurement error mechanism. We should be able to adjust it by anticipating what impact it's going to have. But when it's difficult to trace out, as I showed you before, what is going to be the specific impact because there are multiple mechanisms interacting, then I think what we need to do is rely on adjustment methods. So some of the most common ones that I'm sure many of you already use are these ones. So instrumental variables, latent variable models, multiple imputation, regression calibration. Now, the issue with all these methods is that they require additional sources of data, right? So if you want to use latent variable models, you need at least 3 variables, right? Reflecting the same true or latent and unobserved concept. Now, instrumental variables are really tricky, right? And most of them, they don't meet the conditions that we require them, but, like we could use them to deal with random errors. A validation subsample, so that means like a gold standard for some observations that we can use to calibrate our model using multiple imputation. Or the regression calibration, for that we need repeated observations, so like repeated measurements over the same construct and subjects. Okay, now that's wonderful. If you've got that data, I would encourage you to consider some of that. But again, in reality, very rarely do we have well, not rarely, but in reality, very often we see ourselves in positions where we don't have this data really, and we just have that unique variable that we know is affected by measurement error. And then what do we do? Okay, so in those cases, I think it's still a good idea to try running sensitivity analysis. So the best way, I mean, in my view, the best method, the most flexible, is just Bayesian adjustments. And this handbook from Gustafsson, I think is a true jewel. It's really, really good. So if you get the slides, you can click here and you get to see it. There are some other methods that mix Bayesian statistics, multiple imputation. This one, multiple over imputation, just came recently, and it's quite interesting. This is developed by political scientists. It's a lot easier to use, because the problem with Bayesian stats is that the learning curve is really hard. I've used them in the past, and every time I see myself having to go back and run a Bayesian model, I want to kill myself because the software is so not user-friendly at all, really. So I understand, that this is, it's not a popular avenue, and I think multiple over imputation is more promising. A really interesting method that is really, really simple to use. You really don't need to know what's going on behind it. Is CIMEX. I think this is my favorite method, really. So you can click here, and there is a package to use CIMEX in R. All you need is to feed into your model an idea on how much measurement error you anticipate there to be. So what is the reliability of your measure of your variable? If you've got that, then you can rerun your model and simulate and extrapolate, which is what this method does. And then what I'm going to try to focus on now in the last 5 minutes is talk about what we've suggested in this recounting crime project. So we've created an R package called RCME. So that stands for recounting crime and measurement error. We just published, like the first preprint, but the package is available now. Okay, so what we're suggesting people to do here, in particular, it can be applied to any kind of multiplicative errors, but we design it ad hoc for people using police data, right, for crime statistics, is to recreate, what we're trying to do here with this method is recreate the measurement error process using simulations, so we can adjust the crime statistics that we're deriving from the police and use that instead of the unadjusted crime statistics, right? And again, as before, we probably don't know exactly how much underreporting there is or exactly how much inconsistencies there is between police forces, but what we do use is a range of values and derived from our substantive knowledge of the question, right? Or maybe derived from victimization surveys, and then run a sensitivity analysis. Or if you want a robustness check to assess how much error could you expect, sorry, how much bias could you expect to see in your findings? Okay, so just to illustrate how this works, this RCME package, I'm gonna show you an application that we had where we are looking at what is the effect, we care about that beta one, what is the effect of X, which in this case is collective efficacy. So for those of you who are not sociologists or criminologists, that means basically and roughly, oversimplifying, how much of a community culture or spirit there is in a neighborhood. And that has been posited or argued by many criminologists to be one of the main, or a good strategy to reduce crime. If there is a good understanding of, a good relationship between neighbors, they all look after each other and there is less crime in that area. So we want to look at what is the effect of that collective efficacy on criminal damage rates derived from the police. Criminal damage is this kind of things that you see in properties, right? Like a door that has been banged open when someone was trying to burglar a place, and the burglary never took place, but there was some damage, right? Okay, and what we do is look at London. We look at 982 different postcode areas. So what we do is first we run the naive model using the criminal damage statistics from the police, and then we try to adjust that using this package as a sensitivity analysis. Right. and how we use it is basically, or how this package works, we ask users to consider what is the extent of systematic errors, so the extent of under-recording, the extent of random errors or variability between areas in recording rates. And we also allow to consider differential errors. That's something I haven't covered before, but that basically means whether the errors are correlated to the variable of interest. So in this case, what we see for collective efficacy is that there is more underreporting in areas that there is high collective efficacy, which might be a bit counterintuitive, but that's what we find using victimization survey and estimates. So we see a negative relationship between our variable of interest and the measurement error, really. Okay, but you don't have to use all these different components. You can just feed into this package, your systematic errors. That's the most intuitive one. You can feed in, different ranges of values. And then what you do is you calculate, you create your different ranges of potential measurement errors that you have, you would expect to see. Now you use those and that you've simulated to kind of adjust the crime rate. So because it's multiplicative, we're dividing by the measurement error. And then that kind of takes you back to what you expect to see would be the original Y, or the original true rate of criminal damage. Okay, so this is what we're doing here. Like, first of all, we estimate our naive model. It's this one using police data. And we care about that, the effect of collective efficacy. And we find that just as everyone else has found in the literature, well, most people have found in the literature, we see that there are more collective efficacy in one neighborhood, the less crime, right? So there's a negative relationship. But what we want to see is how robust that estimate is, because we know that crime is affected by measurement error, right? So we try different ranges of systematic errors. One is a scenario where there is no underreporting, no systematic errors. Then 0.86, that would be a scenario where that's actually what we see is like the amount of crime that is reported to the police but not recorded. And then 0.29 is what ends up, of all crimes that takes place, what ends up being recorded, according again to the Crime Survey of England and Wales. We have 3 different values of random error, so like mild, moderate, and severe. And then we have 4 values of differential errors. So the first one, there is no relationship between collective efficacy and the extent of underreporting, and then up to a 3 or 0.3, minus 0.3 correlation between the two. Okay, so what we do now is to assess whether that is robust, is create new adjusted crime statistics using these values, and then seeing, what kind of estimates we find for collective efficacy, which is our main, variable of interest, really, or coefficient of interest here. Okay, so that's when you use that, when you feed all those different values, all you need to do in this package is estimate your model, provide that model in R, and then provide these ranges of values or whatever you want. If you just want systematic errors, you just use that. And then, what the package will do is give you this kind of graph. So it will give you, for all your different scenarios, a measure of what is the expected, what is the estimated effect of collective efficacy, whatever you want to look at on crime. So in this case, we've got in all these different scenarios, that's the naive estimates, as we saw before, it's got a negative effect on crime, collective efficacy. Now, if we look at cases where there is no underreporting, that if there is some random error or some differential error, that doesn't really affect the robustness of our estimates. So if there is no underreporting, we're good. If there is a little bit of underreporting, we're still okay, even if there are strong random errors, and if the error is differential, so it's affecting, collective efficacy is affecting the error mechanism, we can still say that, there is a robust, we can say robustly that there is a negative relationship between collective efficacy and crime. However, when we move to this other scenario, which is what we observe using looking at the crime survey framework ways, when we see that a lot of criminal damage goes underreported, under a third, it's only about like a third of those crimes that gets reported and gets recorded, then in that case, we are fine so long as we don't have differential errors. So long as the collective efficacy is not correlated with a systematic error. If it does, so if we move from 0 here to -0.3, as soon as we move away from there, and then we add a little bit of random error, so we are in these lines, even without random error, we see that when there is a relationship between systematic errors, so underreporting, and collective efficacy, we see that then the estimated relationship between collective efficacy and crime in our naive model is spurious. So it basically means all of this is just a sensitivity analysis to say that all looks robust, so the effect of collective efficacy looks robust unless we've got strong underreporting, and that underreporting is correlated with collective efficacy, in which case, which by the way is what we see, is what we see using a gold standard. In that case, it seems that what we used to attribute to collective efficacy as a good strategy to reduce crime is actually spurious. It's actually due to measurement error in police statistics. Okay, and that's how it works, this package. So let me just wrap it up because I think I've spoken for too long. So apologies about that. So just to say, like many of the variables we use are affected by measurement error. This is a huge problem, really. Like even so, we can anticipate how this problem is gonna bias our univariate statistics. We normally anticipate that that just because crime goes up, police crime goes up, doesn't mean that that's changed in reality, because we know it's affected by measurement error. We cannot trust it, but we don't really know how it affects our measures of causal inference, or how to say, relationships between different variables. Really, that's much harder to anticipate. So I would phrase it as a much bigger problem than what we tend to acknowledge, affecting countless studies, because we can all think about many different variables that we use, right, that are affected by different types of errors or measurement error. And what is a bit frustrating is how little we do about this. And I think I kind of anticipate why we do little about it, because it's kind of, this is a problem more than an opportunity. It's something that we need to deal with. It's not something that will allow us to explore new research questions. It will allow us, right, to increase the robustness with which we explore, the kind of questions that we're already exploring. But it's something that in our view, I think, I've illustrated that could be quite pervasive. So besides improving data collection processes, and that's always something we should aim for, we need to engage much more with adjustment methods, I think. There are many different out there in the literature. Now, many of them, the problem with them is that they're either complex or they require too many different sources of data, so they become impractical, or we cannot really use them. But that's not a reason to despair, because we can still use sensitivity analysis, and that's how we're trying to frame a potential solution that is used by all users, ideally, that at least are using police statistics and many other variables that we know are affected severely by measurement error. in those cases, simulations are a relatively straightforward method that, even though it's not going to give you the true estimate, at least it will give you a sense on how affected, how robust your estimates are when dealing with measurement error in your models. Okay, and I think I'll leave it there. Thank you very much. Cheers.
Thank you so much, Jose. That was really wonderful to see all that complexity distilled in under 50 minutes and lots of interesting figures and graphs. I think you can see in the Q&A there already are quite a few questions. So I didn't want to interrupt you. I thought you could maybe, can you see?
Yeah, I think I see them. Right, so should I go over them then?
Yeah.
Over these question and answers? Okay, so we see that 1 and 2 not biased, right? That's what I used to think, right? I mean, there's scenario number 2, right? I mean, like, but what is always a surprise is how measurement error, right, in the explanatory variable can lead to attenuation bias, right? I mean, that's why is that surprising? I think it's because many people see, and I used to be think the same way. We tend to think this as missing data that is missing completely at random, of which, when we know that, it doesn't affect your, doesn't lead to bias. But in this case, measurement error, when it's random, it does. Yeah, it's counterintuitive, but that's hopefully, one of the lessons of today. Okay, next question. The randomness of explanatory variables underpins randomized controlled trials. Since in your example, you cannot determine results, how do we overcome or account for it? Right, okay, so if you can expect random errors in your trials or any kind of analysis, really, what you can do is, if you can repeat the observation process, or if you've got, well, if it's random, just repeating the observation process should allow you to calculate the reliability ratio in your measure of interest. If you've got a gold standard, even better, right? I mean, because then you can also look at systematic errors. But repeating the same observation process, you should be able to calculate the reliability ratio. And then if you know the reliability ratio, then you should be able to adjust directly without any kind of like adjustment methods. So let me just go back to this little piece of math that I have here. When we've got measurement error in the response variable, I'm not sharing my screen, right? 1 second, let me just go back to share it. This is what I was referring to. So this piece of math here. So when we've got measurement error that is random on the explanatory variable, we are going to end up with this kind of bias. So the beta estimate that we obtain is going to be affected by this chunk, which is the variability of the true construct divided by the total variability. So the true plus the noise, so the observed variability. And this is what is known as the reliability ratio, right? So if you can calculate that by taking repeated measures on the same subject, and hopefully if the true value stays stable, right, stays the same, so ideally, you don't repeat those measurements like over different years and then the subject has changed, then you should be able to calculate that. And then if you've got that, you can just adjust, so divide the estimate that you obtain by that reliability ratio, and then you retrace or recover the true value. Yeah, I think that's what I've seen done in many different applications in the literature. So hopefully that's useful. I mean, I'm still sharing my screen. I don't know if I am.
Sorry, Jose.
What do you see? Do you see my screen or?
So we weren't seeing your screen. So we just saw you, and we're still only seeing you. But I think that's okay.
No. Okay. All right. Okay. Wonderful.
Okay.
Okay. All right. Let me just very quickly. Let me. So I messed that up. You should have told me. Okay. Can you see this one now? This screen.
Yes.
So the reliability ratio I was talking about is this one here, right? So if you can calculate that, that's the variability in the true value divided by the observed variability, the true variability plus the noise. That is the reliability ratio. You can calculate that using repeated observations. If you've got that, then you can adjust your estimate of the slope with that, and then retrieve the true one. Sorry, I'm so awkward. I've been using, well, I suppose I use Teams more than Zoom. That's my excuse. Okay, and next question. So, wow, I'm okay. We've answered 3. Okay, the next one is log transformation, a common and prioritized way to reduce the impact of errors when the analysis sticks to regressions. Practically, are there any drawbacks or concerns when using this transformation over estimation? Yeah, that's a very good question. Actually, I would say I mean, this is kind of like a rule of thumb, right? I mean, so ideally, we would think a bit carefully, but for what we've seen, if the measurement error that you expect is multiplicative, right, then log transforming is a good idea, because normally, what we've seen is that, the bias is way more pervasive when the errors are multiplicative than additive. Now, that doesn't mean that the bias is always going to disappear. In some instances, it will disappear. In some instances, there will still some bias. And now that opens, potential side effects, which is, I think, what you're asking for about. In some cases, we use log transformations because we want our response variable and the residuals to be normally distributed, right? When we've got right-skewed data, like duration data or count data, we normally use Poisson models, Weibull models, right? Which in the end are just log transformations, really. So our variables, our outcome variable is normally distributed. Now, if we've got a variable that is already normally distributed and then we log transform it, maybe we are moving away from normality and making it left skewed artificially, right? So that could be one instance when, log transforming to prevent measurement error might end up doing, making things worse. So, like, I suppose if you want to be careful, you need to think about that too. I was just presenting this as a kind of like rule of thumb. But yeah, in my experience, that kind of works really. Very rarely have I found count data, duration data that is not right skewed, that doesn't look better, more normally distributed when we log transform it. That could be the case. So do you have something else in mind, or did I answer your question? There could be other implications we haven't thought of, but I think that's the first one that springs to mind, really. So can the package be used on other psychological constructs? Yeah, I mean, it's annoying, really. Ideally, there should be a package out there that will allow you to do this for any kind of measurement error models or mechanisms that you expect to see. What we've done in this package is, and because it's our first attempt, really, is to tailor the adjustment process to the kind of errors that we see in police statistics. So, what we're doing is simulating errors that are multiplicative and then are systematic, and then can also be random and differential. So if you expect your psychological constructs to be affected by multiplicative systematic errors, then yes, I think definitely this package, you can reuse it, really. I mean, because that's what the kind of measurement error mechanisms that we're dealing with, we're tackling. If you expect your measurement error processes to be additive, then no, don't use it. Or what I would suggest you do is create your own simulations. Hopefully at one point we'll be able to expand the package so we facilitate this process, right? I mean, all that goes behind the scenes in the package can be replicated for non-multiplicative models. But at the moment, it isn't really, because we've kind of focused on police data, which is what the project was about, which is how we got the funding, really. But hopefully, we'll be able to get some more funding and keep expanding, really. Okay, and I'm now looking at this other question. May I ask if your slides will be made available? Of course, yeah, it would be absolutely my pleasure. So I've been spamming Tarani with different versions of the slides. I'll send you the latest version, okay, Tarani,
yeah,
and then you can distribute that.
That's works. Right. We'll host it on the Methods Hub website, the recording plus the slides. So yeah, definitely yes.
Excellent. And then there's another question about bootstrapping. I don't think. Okay, so bootstrapping is a fantastic technique that is often, underused, really. It could be used much more than we really use it for, really. But in this case, no. I mean, there is no resampling methodology here, so it's just simulating. In a way, like the crime rates that we get from the police are untouched up to the point after we divide them by the simulated error. So what we're doing is simulating some errors, so making up some data, really. So we're simulating errors according to how we expect those errors to be distributed. So normally distributed with the variability equals to how much random errors we anticipate, with a mean equal to how much underreporting, and maybe also that distribution is correlated to your variable of interest if there are differential errors. So that's what we tell R to create, right? I mean, out of the blue, really. Those are simulations. And then once we've got the error term, we use it to divide as the denominator in a division of the observed crime rate from the police. So in a way, we take the crime rate from the police, and then we take away the measurement error by resimulating it and then dividing by that. And why we divide is because it's multiplicative. So that's kind of like how we adjust for that using simulations. I haven't done a very good job really at explaining it. But yeah, there is no bootstrapping. I mean, that's the short answer. And then would you think making sensitivity analysis essentially? No, yes, great question. Oh yeah, that's been, I'd love to, but I'm sorry, I'm gonna finish it. Essentially in all journal article submissions could be a solution to the problem posed. Absolutely, I think that's a must, really. I think we really need to steer away from quantity and focus on quality in academic research. And it's easy to say, right? But of course the incentives are in all of us to publish or perish, right? Publish as much as possible and publish as quickly as possible. And also that those are incentives that editors have, right? I mean, it's not just us, like the researchers or the authors. So editors need to need papers, right? So requiring all this sensitivity analysis, what it does, it makes it more cumbersome, the process, right? But it's absolutely essential because at the end of the day, there is a lot of noise out there, a lot of evidence that is very questionable, right? I mean, measurement error is one of the problems, but of course, like now we've got, we're living through the causal revolution really, and we know how confounding factors can also, they are lurking everywhere when you're using observational data. So we should also use sensitivity analysis to account for that. And same with missing data. Missing data is everywhere really, or selection bias. So absolutely, I agree wholeheartedly. The issue is how do we change the incentives really in this messed up system that we have in academia of publishing, so we care more about quality and less about quantity. But yeah, I'm 100% with you there. And then the last question: is it a good practice to calculate or adjust for measurement error Bayesian for data other than criminal, such as normals? Yeah, I think it's a good practice really. I mean, like but Bayesian stats, unless you've used them before, I wouldn't send you, because it can be a rabbit hole. Like I've used them in the past, and I'm not like, unless you're a geek, I'm not really a geek, and I struggle with it. I struggle most with the software, really. I've used Stan, I've used Winbags, Openbags, and I still struggle with most of the software. So the returns is a steep learning curve. So if you really want a challenge, by all means, learn it, because that allows you to adjust for everything. Like they are as flexible as you want them to be, right? You can use strong priors, you can use auxiliary data. It's just fantastic, really. So the future is definitely Bayesian, but at the moment, I find it very complicated and not user-friendly. And we shouldn't expect everyone to use it, really. And then there are other methods. I think one method that is really easy, simple enough. If the measurement error that you are dealing with is relatively simple, like random errors, misclassification problems, even systematic errors, but it's not like 100 different things or many different mechanisms at once, I would recommend that you use CMEX and take a look. When Trani sends you the slides, there is a link to the paper, but there's a very good package in R that works beautifully. That even if you don't have, if you just know how to use R a little bit, you are not an expert in R or programming at all, you can still use it. You learn, like they've got a paper on the R journal on how to use that package, and it's very, very straightforward, and it works really well. So if for simple kind of like only one mechanism, like random error systematic, I would really recommend that you use CMEX. It's the easiest and quite effective. And then you always assume X, Y, and X are linearly related. Yeah, good question. How about if Y and X are non-linearly related? How could be the impact? Okay, well, yeah, I've assumed that they are linearly related because that's the simplest, cleanest possible scenario, right? So this is complex enough, right? I mean, for an introduction. So that's why I focus on the simplest possible method or outcome model, which is simple linear regression. When you add more variables, then things get much more messy. The impact that you can expect impacts or biases that have to do when the controls that you're using in your model are correlated with the measurement error or with the true value of the variable that you care about, then that can be affecting the bias. So things get more complicated. And of course, when you've got nonlinear models, that's just crazy, really. Like it's really, really hard to trace out. Normally, it's almost very hard to trace out algebraically. So what I recommend that you do, if you want to see exactly what impact that could be having on your models, is use simulations, really. And try to recreate the error term, and then throw that into your model, change the variable that you want to use, and re-estimate your model with that variable that has been adjusted using simulations. And that way, you can kind of like recreate what would be the impact. But do it algebraically, it can be a nightmare, really. And in many cases, there is no closed form. It's just impossible to trace out. Measurement error Bayesian. I think that's. Have I answered all the questions?
I think yes. Yeah, I think you've done a great job, Jose. I think you've answered all the questions.
I think so, right? Or did I miss anything?
No. I think you've gone through all of them.
Right. But these are fantastic questions, really. I mean, like, it's good that I've been working on this for some time because, these are like, really like spot on, really.
I did have questions of my own, especially because you mentioned missing data processes, and I was immediately thinking about not missing it at random selection processes. But I will corner you a different day, Jose.
Right.
I just want to thank you so much for taking the time and effort to give us such an interesting talk, and also for sharing your slides, because I think it's such wonderful work that you've been doing, and developing this package as well, so people can intuitively see to what extent their coefficients are being biased and by these measurement error issues. So for people attending, thank you so much for attending. Next month, we have another method sub-seminar also on the issue of biases in observational data. It's being given by Professor Lo Hao from the University of Hong Kong. So please do attend. Please do look out for our email invitations to the seminar. But I just want to thank Dr. Jose Pina-Sanchez once again for a wonderful seminar.
Yeah, my pleasure. Thanks a lot, everyone. See you. Thanks, Torani. Bye-bye.
Bye.
Cheers.